Good morning, all. In this video, I will explain the stacked ball experiment. This is a fantastic experiment that you can do with the two balls, say with a basketball and a cricket ball. So, if you have two balls that is stacked together, the big one is kept in the lower side, and if you drop it from a height h, after collision with the ground, the big ball will move up with velocity v, and that velocity will be same as that of the velocity before collision if you are considering the collision elastic. And what happens to the small ball? The small ball will rise to a height of 9h. The velocity of small ball after collision will be 3v, and it will rise to a height of 9h. I will demonstrate this experiment and I will explain the theoretical.
കണ്ടില്ലേ ഇനി എറിയൊന്നല്ല ചെയ്യുന്ന കേട്ടോ, ഞാൻ വെറുതെ ഡ്രോപ്പ് ചെയ്യാം. ഇത് ചെയ്യുമ്പോൾ ഒരിക്കലും കുട്ടികളെ അടുത്ത് നിർത്തരുത്. മുഖത്തൊന്നും എടുത്താൽ നല്ല വേദന ഉണ്ടാവും കേട്ടോ. പ്രത്യേകിച്ച് ഇത് സോഫ്റ്റ് ടെന്നീസ് ആണ്. ഹാർഡ് ടെന്നീസ് കൊണ്ട് ചെയ്യുകയാണെങ്കിൽ ചുറ്റുവട്ടം ആരും നിർത്തരുത് കേട്ടോ. ഇതിന് ഭയങ്കര മൊമെന്റത്തിലാണ് തിരിച്ചു വരിക. ഓക്കെ, അപ്പൊ ഒന്നുകൂടെ കാണിക്കുക, എന്നിട്ട് നമുക്ക് ഇത് എക്സ്പ്ലെയിൻ ചെയ്യാം.
To explain the theory of this experiment, we just need the idea of collision in one dimension. Okay, so consider two balls having masses m1 and m2, and they are moving along a straight line with velocities u1 and u2. If u1 is greater than u2, after some time they will collide, and after collision let the velocities of the two balls be v1 and v2 respectively. Then, since this collision is an internal process, considering the two masses as a single system, we can apply conservation of momentum. That is, the initial momentum or momentum before collision is equal to momentum after collision. Momentum before collision, the first ball have a momentum m1 u1 and the second ball has a momentum m2 u2. The total momentum is on the LHS, and the RHS we have the total momentum after collision m1 v1 plus m2 v2. And if we assume that the collision is perfectly elastic, then we can apply conservation of kinetic energy, that is half m1 u1 square plus half m2 u2 square equal to half m1 v1 square plus half m2 v2 square. We can rearrange equation 1 like this and name it as 1a. Okay, you group terms having mass m1 on one side and terms with mass m2 on other side. In the same manner, you can rearrange equation 2 and call it as 2a. Now divide these equations 2a and 1a. You will get u1 plus v1 equal to v2 plus u2. I will rearrange this to write in this manner: u1 minus u2 equal to minus of v1 minus v2. u1 minus u2 is relative velocity of the balls before collision. v1 minus v2 is relative velocity of the balls after collision. So this is a very important result in one-dimensional collision. Relative velocity before collision equal to negative of relative velocity after collision. Okay. Now we can express v2 in terms of u1, v1 and u2 from equation 3, and substituting that value of v2 in 1a, you can write like this, and you can solve for v1 as 2m2 u2 divided by m1 plus m2 plus m1 minus m2 into u1 divided by m1 plus m2. Similarly, you can express v1 in terms of u1, u2 and v2 and substitute in 2 in 1a, then you will get v2 as 2m1 u1 divided by m1 plus m2 plus m2 minus m1 by m1 plus m2 into u2. So these are the final velocities of the balls in terms of their masses and initial velocities. Okay. Now, coming to our experiment, here you have a big ball and a small ball. After collision with the ground, the big ball is moving up with velocity v. At the same time, the small ball is actually coming down with velocity minus v. During the process of collision between big ball and small ball, they are actually moving in the opposite directions. So the big ball is moving up with velocity v, small ball is moving down with velocity minus v. At that instant, the collision happens. So before collision, what is the relative velocity? Relative velocity before collision is minus 2v. If I am considering the relative velocity of small ball compared to big ball, relative velocity is vs minus vb. Vs is actually downward minus v. This minus and vb is v. So it becomes minus 2v. And as per the equation 3, we have relative velocity before collision is negative of relative velocity after collision. Therefore, relative velocity of small ball after collision is negative of minus 2v, and that is plus 2v. So after the collision, small ball is moving with respect to big ball with the velocity 2v, that is in the upward direction. Now, if we assume that this big ball has a very large mass compared to small ball, that is m is very much greater than small m. After collision, this big ball will move upward again with the velocity v. That is, the collision is ineffective for this big ball. If this big ball has very large mass compared to small ball, the collision doesn't affect the big ball and it will still move upward with the velocity v. In that assumption, actual velocity of small ball will be 2v plus v, because the velocity of small ball compared to the big ball is 2v. Big ball is actually moving up with velocity v. From that frame, the small ball has a velocity 2v, means that actual velocity of small ball with respect to ground is 3v. I hope it is clear. So the actual velocity of small ball after collision will be 3v. Relative velocity is 2v. If the mass differences are infinite, then the big ball after collision will move upward with velocity v itself. So compared to that, the velocity of small ball is 2v. So compared to ground, the velocity will be 3v. So this is the figure. So before collision, the big ball is moving up, small ball is moving down. Then after collision, the big ball still moves up with velocity v, assuming that they are having infinite mass difference, and the small ball will move up with velocity 3v. Okay, what will be the height attained by the small ball? Height attained is initial velocity square divided by 2g. This is from equation of motion. But here the velocity of small ball is 3v. So 3v square is 9v square by 2g. But what is v? v is the initial velocity of big ball. That is the velocity attained by a body when it is dropped from a height h. It is root 2gh. So you can substitute for v as root 2gh. So v square becomes 2gh, 2g cancels. So h prime is 9h. In terms of the initial height h, the final height attained by the small ball is 9h. Now, if you have 3 balls, then if they are having infinite mass differences, the first ball rebounds from ground with velocity v. So I can say that v1 is equal to v. The second ball, that is blue one, for the second ball, relative velocity after collision equal to relative velocity before collision, the magnitude is 2v. Therefore, actual velocity is 2v plus the velocity of the first ball, that is 3v. This is we already proved. So v2 is 3v. This is the case of 2 balls. What happens to the third ball? For the third ball, relative velocity with respect to second ball is 4v. How? Because the second ball is moving up with velocity 3v. The third ball is moving down with velocity v at the time of collision. Therefore, relative velocity is 4v. The same relative velocity will be there after collision also. So, after collision, the relative velocity is 4v. So, actual velocity is 4v plus 3v, because this relative velocity is with respect to second ball. So, when you viewed from second ball, the third ball is moving up with velocity 4v. So, for an observer on the ground, the velocity of third ball will be 4v plus 3v. It is 7v. Therefore, v3 equal to 7v. The height attained by the third ball will be 7 square, that is 49h. 49h. If you consider 4 balls stacked together, the relative velocity of fourth ball with respect to third ball will be 8v, because the third ball will move upward with velocity 7v after collision. The fourth ball coming down with velocity v, therefore relative velocity is 8v. After collision also, the relative velocity will be 8v. Therefore, actual velocity will be 8v plus 7v, 15v. Fourth ball will move up with velocity 15v. So, the height attained will be 225 times the initial height. And if you go like this, using mathematical induction, you can say that the nth ball will attain a velocity 2 raised to n minus 1 into v. 2 raised to n minus 1 into v. So, if the initial height is 1 meter, velocity, you can calculate it as root 2 gh. It becomes 4.42 meter per second. 4.42 meter per second. And if you consider 11 balls stacked together, the velocity of 11th ball is equal to 2 to the power 11 minus 1. That becomes 2047 into v, that is 4.42. That becomes 9047 meter per second or 9.047 kilometer per second. It is less than escape velocity. And if you consider 12 balls stacked together and dropped from a height of 1 meter, the velocity attained by the 12th ball is 18.099 kilometer per second. It is greater than escape velocity. So that ball will escape to infinity, provided the 12 balls should have infinite mass differences and all collisions should be elastic. Okay, now we will see what happens if the mass differences are not infinite. Okay, so consider this case. If the mass m1 is m and m2 is m by 2, then what will happen? Before that, I will explain the condition we already discussed, that is the mass differences are infinite. We have to use these two expressions. This I already explained. v1, the final velocity of first ball, v2, the final velocity of second ball. Here I will take the first ball as the big one and the second ball as the small one. And I assumed that this m is very much greater than m. Then what I can do is m1 plus m2, approximately I can take it as m, since this m1 is very much larger than m2. So you can neglect this m2. Also m1 minus m2, you can approximately take as m. And u1, the big ball is moving up, so it has velocity v before collision. And the small ball is coming down before collision, so its velocity is minus v. So final velocity of big ball v1 is 2 into this equation. m2 is m and u2 is minus v divided by m1 plus m2 I will approximate as capital M, plus m1 minus m2 is again capital M into u1 is v divided by capital M. So this m and m will cancel, you will get v. Here this m by m, small m by capital M, since small m is very much small compared to big M, you can take it as approximately 0. This ratio you can take it as approximately 0. And under that condition, V1 is approximately capital V. That is, the final velocity of the big ball remains the same as that of initial velocity, only in this condition. And V2, substituting here, 2 into M1 is capital M, U1 is V, M1 plus M2 is approximately capital M, plus M2 minus M1 is minus M, U2 is minus V, divided by M1 plus M2 is M. So you will get 3V. So the velocity of small ball after collision becomes 3V. Again, you can check the relative velocity V2 minus V1, that is 2V. Okay, relative velocity is always the same as that of relative velocity before collision. So actual velocity of small ball is 3V after collision, considering infinite mass difference. This is the case we discussed. Now, if you consider the big ball has mass m and the small ball has mass m by 2, only half. Okay, not infinite mass difference, just the half mass of big ball. Then big ball is moving up with velocity v, small ball is moving down with velocity minus v during collision. Then final velocity v1, you can substitute these values in these expressions 5 and 6. v1 becomes minus v by 3 and v2 becomes 5v by 3. So the actual velocity of small ball is just 5v by 3, not 3v. That is, it's just 1.67v. And the height attained by the small ball will be the square of this quantity, 2.79 of initial height. Not 9h, it is just 2.79h. If you are taking two balls, one having mass half of that of the first mass. Okay, if you have two masses with masses m and m by 2, the height attained by the small ball will be just 2.79h. Now, if you are taking two masses, first one is m and the second one is m by 4, then you can calculate v1 as v by 5, v2 as 11 by 5v. Okay, so again you can see that the relative velocity is 2v and the actual velocity of small ball is 11 by 5v, that is 2.2v. So height attained is 4.84h, almost 5h. Okay, so if you are taking two balls with the masses m and m by 4 and then stacked together and dropped from a height h, the small ball will rise to a height approximately 5h. So in the same manner, you can calculate the height attained by the small ball by substituting the masses here. Okay, thank you.